In part one of this review, or mini review, didn't intend it to be a pun, but the mini review of the miniVNA. This is the miniVNA Tiny Plus. Got it from China. In part one, we looked at the use of this, setting it up, calibrating it, and using it to measure both reflection and transmission parameters of RF networks. What we're going to, at least for the first part of this part two, is actually looking at the miniVNA itself. Now, I'm not a big fan of teardown videos, and so I don't tend to tear my equipment down. It's not that I don't sometimes watch them. It's kind of interesting to see sometimes what's inside of them, but I am much more interested in, do they match the published specifications, and how easy are they to use, and how useful are they in a lab. So I'm not going to try to tear this unit apart or anything like that, but what I am going to try to do is to measure its characteristics and then see if I can find the specs, which I right now do not know where they are, for this particular unit, and see how those compare. So what I have is a mini circuits 6 dB attenuator on the DUT output. And the reason that I'm doing that is to reduce the level. In part one, or in the introduction, I think it was, I talked about the need to protect your equipment from itself. So I'm using a 6 dB attenuator for two reasons. One, that helps to provide a more constant 50 ohm impedance to the DUT output, and it tends to lower the output level, which tends to protect the instrument that we are driving. So what is that? I have the other end of the attenuator from the miniVNA output connected to this Instec DSP 730 spectrum analyzer. Now, over here, I am using a DC block. That protects both instruments, because DC can't flow out of the Instec unit into the miniVNA, nor can DC move from the miniVNA to the Instec. But in this case, you don't really need that, because neither of these put out DC voltages. But if you are working on an unknown piece of equipment, or a piece of equipment where you're not sure what the DC voltage level is, of course, first you should measure it. You shouldn't just depend on a DC block. But you should always have a DC block in place, at least initially, until you can verify that the instrument is not producing any DC voltage. Now, on the screen is the see if I can get in a little bit closer without it going out of focus. There, hopefully that'll work. Now, what we are doing is we are beginning at 0, or essentially DC. I think this actual unit only goes down to like 150 kilohertz, out to 10 megahertz. And the reason that we're doing that span is we're looking at the output of the unit, and we have it in free run. I'll show you the software in a little bit. It's in free run. This unit is in peak hold mode, and right now the resolution bandwidth is set to a megahertz. And I'm doing that deliberately because I'm not interested in fine resolution. What I'm trying to determine is what is the output level of this miniVNA. That might be important in some cases where you're testing a circuit, you might need to know what the output level of this is, and then we will compare that if we can find the specs on this unit. I frankly haven't even tried to look for them, and since it doesn't come with a manual, you can't just look in the back there. Anyway, so what this is actually showing is, since this is a 10 megahertz span, this is a megahertz, which is about the beginning of the miniVNA scan. And you'll notice that the output at that level is about minus, about 20 dB. Then the output rises to just a little above minus 10 dB. Now remember, we have a 6 dB attenuator in place. So what that tells us is that this unit is putting out about minus 4 or minus 3 dB or dBm of power, at least over the range from about 3 megahertz and up. Now we'll look at another span up maybe around 1 gigahertz and do the same thing, and then maybe around 3 gigahertz and do that as well. What we're trying to do is to find out how flat is the output, and does it have any significant peaks and dips that we can find. Now, why am I using peak hold? Well, remember that the miniVNA is scanning at the same time that the spectrum analyzer is scanning, and they are not synchronized. Now, this particular spectrum analyzer does not have a trigger, nor is there an output from the miniVNA that you could trigger on. So there's no way to synchronize these units. What you can do is leave the unit running for a period of time, which is what I've done. So this is the signal that we're getting up to 10 megahertz. Now let me show you if I start it over, what I'm going to do is I'm going to go trace to clear and write, and you see there it just gets an occasional burst of energy and then it disappears. So if you're not familiar with the difference between clear and write and peak hold, go back and watch my series of videos on spectrum analyzers. But at any rate, what peak hold does is it takes the peak of each signal and holds it there. So basically it fills in. Well, I'll show you how that happens. You see how it's filling in as it sweeps. And that's how I got the signal that I looked at earlier. So now let's go look and see what the miniVNA software sees. So this is the miniVNA software. It's called VNAJ, and if you watch the first part, you'll know where you can download this and so on. It is appears to be open source. I'm not sure that they try to adhere to the open source rules. But at any rate, it's freely available on the web from various sites, but it's produced, or at least the project is managed by a German engineer or scientist. At any rate, this is the VNAJ software running the miniVNA Tiny Plus. Here is the return loss, and you see it's around minus 32 dB. And remember, we have a 6 dB attenuator in the line, so you need to take that into account. And then down here is the SWR, and you notice that it's well below 1.1. Now understand what's happening here is the miniVNA is looking at the input of the spectrum analyzer and is saying, okay, it's pretty good. It's not great, but it's pretty good. And the SWR is certainly within an acceptable range. So now let's go up and repeat the experiment at a gigahertz, and then maybe around 3 gigahertz, which is the frequency limits of the miniVNA. Now we're repeating the measurements. Everything else is the same, but we're doing this at a gigahertz. We're basically scanning from a gigahertz on the left to 1.001 gigahertz on the right. And once again, the reason we're using a relatively narrow span is so that we can accumulate a good sample in a reasonable period of time. So let's come back in a few seconds or a minute or so, and when this is filled in, and then take a look at the final results. Well, here is after several minutes of accumulation, and part of the problem is that this spectrum analyzer uses an auto resolution bandwidth above a gigahertz of 30 kilohertz. Now earlier you may remember I was using a megahertz of bandwidth, so that's the reason why there are still some gaps in this, but you can see the average. It's about minus 20 dBm. Now remember earlier it was about minus 10. This is one reason why that you need to calibrate the unit is the actual oscillator that is used to drive the circuits. In other words, the oscillator that comes out on the DUT pin varies over frequency. It's not a very good oscillator, but it doesn't have to be, because the unit, the miniVNA, compensates for that. It gathers the data when it's calibrating, and I don't want to get too deep into this, but basically it levels out the variations in the output level with variations in by putting in compensating values that it has stored during the calibration process. Once again, if you're not familiar, well, there you see it just happened to hit that little 30 kilohertz glitch there, finally filled in. At any rate, what I'm now going to do is change cables and see if we get any different result. So here is the trace with a different cable, slightly higher quality cable. This is a cable that's rated out to about 5 gigahertz, and I just wanted to make sure that we didn't have any issues. Now the cable I was using was rated to 3 gigahertz, so I shouldn't have expected much difference, but you see, well, it is consistent with the earlier, in that what we're looking at is the average output level of the miniVNA. So now what I'm going to do is remove the DC block, because I have determined that there's no DC in any of this, and we will check that, and then we will remove the attenuator. And here is the results. I haven't let it finish filling in, but you can get the idea without the DC block. Now what I'm going to do is change instruments. Instead of using the Instec, I'm going to use the Rygel spectrum analyzer. Now I'm using the Rygel, and you may notice that the reference level is still 0 dBm. It's showing a level of about minus 16 dBm, maybe a little more than, well, let's say minus 16. And we could measure this, but we're just looking for general information here. And one reason that I wanted to switch to the Rygel is to see if there would be much difference, but also to get around the problem I was having with the Instec. The Instec was really designed to be used in the GSM band, that is around 2.4 gigahertz, and for cell phone use, which is the old GSM standard was of course 30 kilohertz. So above a gigahertz, it automatically goes into a 30 kilohertz resolution bandwidth. That's one of the downsides of that generator. With the Rygel, I can set the resolution bandwidth to a megahertz like I was using earlier, and so it's much faster. Let me show you. I'm going to do trace type clear right, and you see what's going on there. And then if we go to max hold, notice how quickly it fills in. And that's partly because the Rygel is a much faster instrument. In other words, it scans a lot more times per second. And I'm using a 1 megahertz resolution bandwidth. So if the signal falls anywhere within that megahertz, the Rygel will add it to the max hold. And so it quickly fills in. Now, the next thing I'm going to do is go see if the input of the Rygel is, remember, we're measuring two things here. We're looking at the output of the miniVNA, but we're also looking with the miniVNA at the input of the spectrum analyzer. So let's go look at that. Well, as you can see, the SWR of the Rygel is essentially the same as the Instec. It's pretty good. It's below 1.1 to 1. It's around, well, let's measure it. Okay, it's saying the SWR is 1.07 to 1. And the return loss is minus 29 dB. So that is the input to the Rygel at a gigahertz. Now I have switched over to the Siglent spectrum analyzer, doing exactly the same thing, resolution bandwidth of a megahertz, sweeping from 1 gigahertz to 1.001 gigahertz, with a max hold trace, and we're seeing that the output of the miniVNA is about minus 16 or minus 17 dBm. However, there is one interesting thing that I want to show you on the display of the miniVNA. You may notice, let me turn this down just a little so you can see where we are, that the SWR of the Siglent input is reading 1.1 to 1. If you remember, both the Rygel and the Instec units had an input SWR less than 1.1 at a gigahertz. The exact value is 1.12 to 1. Now, that's not a really terrible SWR, but what it indicates is that the match of the Siglent at a gigahertz is not as close to 50 ohms as the Rygel and the Instec. This is something I had never tested before, but it's an example of why a piece of equipment like this can sometimes tell you things that you didn't otherwise know. Now, the return loss is also different. It's minus 24.6. And so the next thing I'm going to do is I'm going to go up to closer to 3 gigahertz. I think I'll use about 2.5 gigahertz, so I won't be right at the frequency limits of the... I want to do something that's slightly above the ISM band, so I'll probably use around 2.5 or 2.6 gigahertz. And now you'll see why that I wanted to start with the Instec. It goes to 3 gigahertz, as does the Siglent, but the Rygel does not. So here we're going to go back and take a look at the Siglent, but we're going to change our frequency up to something above the ISM band. And here you see the display in clear right, and then we'll go to max hold. Let me zoom in a little bit more on that. Okay, now as you see, we're getting about minus 15 dBm. And I can tell you that the SWR is reading about the same, about 1.12. Let me take a look here. And yeah, 1.12 to 1 at 2.6 gigahertz. So, what have we found out? Well, we have found out a little bit about the Siglent. It turns out its SWR at its input is not quite as good as the Rygel or the Instack at a gigahertz. We haven't compared them at any other frequency. But at 2.6 gigahertz, the SWR on the Siglent is almost identical to what it is at 1 gigahertz, so we have no reason to believe that it would vary much away from that. But what this shows you is how you can use an instrument like the miniVNA to check other instruments, or you can use other instruments like the Instack, the Rygel, and the Siglent spectrum analyzers to check the miniVNA Tiny Plus. Here is the Siglent operating at 2.6 gigahertz. The start frequency is 2.6 and the stop frequency is 2.601 gigahertz. We'll now switch to the trace menu. We're doing a clear write. Now we're going to do a max hold. And this is without any attenuator on the output, no DC block and no attenuator. So it's just straight out of the miniVNA. And you'll notice that I have a marker in the center. We'll turn that marker on. Well, we'll do a peak detect is what we'll do. And you will see that at 2.6 gigahertz, the output of the miniVNA is minus 8.49 dBm. Now I'm going to go back down to about 100 megahertz and do the same test on the Siglent and see what it reads without any attenuators or DC blocks. And here is the Siglent at 100 megahertz, spanning a megahertz, in other words from 100 to 101 megahertz. Now we'll go to max hold. And we will do a peak reading. And here we read 2.98 dBm. So the tracking generator, if you will, in the miniVNA puts out about minus 3 dBm at 100 megahertz, and it puts out about minus 8 dBm at 2.6 near the top of its range. So this gives us a characterization, but now I do want to show you one last thing about the Siglent at this frequency. At 100 megahertz, the SWR is 1.11 on the Siglent, and the return loss is minus 25.42. So those are comparable to what we were getting with the Instack and the Rygel at 100 megahertz. So I'm not going to try to get into a review of the Siglent spectrum analyzer or comparing it with the Rygel or anything, but I did want you to see the results at this lower frequency. I'm very happy with the miniVNA Tiny Plus. I'm going to do perhaps a couple more experiments, and if so, I'll add them to the end of this video. I know I'm going to be doing a lot more in the future with this. I really like this miniVNA Tiny Plus. I certainly want to give kudos to the author of this VNAJ software, as well as to the people who developed this. Now, as I pointed out at the very beginning of part 1, I bought this on Amazon from a vendor in China. And according to their specs and according to Andres Spies, this has superior reference stability to the original miniVNA Tiny. So, those of you that might have one of those originals might want to do some similar experiments. I'm not going to try to compare the two, partly because I just don't see any reason to go buy two different ones that are essentially the same unit and just to compare the frequency stability or the temperature stability. But I think what I will do at this time is thank you for watching. Hope that you have gotten something out of this, and if you have some comments or suggestions on where we might go next, please post them in the comments. But basically, look forward to some more. I don't know if I'll add any to this video, or I'll just wait until I have enough for another entirely separate video. But at any rate, in the meantime, have a nice day.